The topic of this video is to find area between two curves. And we've done that somewhat. We've looked at a function and its relationship to the x-axis, or y equals 0. But now it's time to look at more graphs that perhaps don't intersect with the x-axis but intersect with each other. So if we're asked to find the area between two curves, make sure you know that that has to be a positive value. All right, we're going to look at two situations of area between two curves. So we're going to get some background on integration with respect to x first, then we'll look at integration with respect to y. All right, graphically, integration with respect to x means that we have two functions, okay, and just randomly drawing two graphs. And perhaps both of them are parabolas, okay, where the top function we'll call f of x, and the bottom function here underneath we'll call g of x. We're interested in finding the area between these two curves. And again, remember that area means we're looking for a positive answer. Okay, if we're looking for the area between these two curves that naturally intersect, and we'll call this intersection, at least its x value a, the left bound, and the x-coordinate of this point of intersection b, okay. If we're looking for the accumulated area between a and b, we're going to use rectangles to help us find that area. Ultimately, we're going to use the sum of the area in an infinite number of rectangles to find that area. And the integral is what's going to help us actually calculate this area. All right, but the background on the setup of the integral goes like this. If we were to inscribe from A to B an infinite number of thin rectangles, find the area in each and every one of those rectangles, and then sum them, okay, we would have the area between these two curves. So what we need to do for our problems when we get there is we need to see a graph of the two functions that are intersecting, and we need to draw in a random rectangle. So just imagine, if you will, that this is a rectangle, that it has some width and it has some height. Even though it looks like a segment, we're going to pretend that it is a rectangle. Okay, so if we were to find the area in this one little rectangle right here, looks like a segment, but imagine it to be a rectangle. Okay, let's get a representation for that area. So the area in this rectangle is its base times its height. Well, if we think about the base is this horizontal distance right here. We're going to call that base delta x, a change in x, or dx. But we'll call it dx. If we want to find the height of this rectangle so we can multiply it by dx, okay, then we would have to know what this y value is, what this y value is, and then subtract the two. So if we know the high y value, f of x that is, and if we know the low y value, g of x that is, we can subtract and we would get a representation of that numerical height. Okay, so just consider, if you will, that this is the x value right here. This x value generates this g of x value, and this x value gives this f of x value. Okay, so if we were to take the height here and get it by taking f of x and subtracting g of x, that's the difference of two y values. Okay, we would then have the height of that one rectangle. If we multiplied it by the thickness, or dx, this would give us the area in that thin rectangle. So this is our arbitrary rectangle that results in this area. So what's left for us to understand is that if we want to find the area in the infinite number of rectangles that are in here, we would have to sum them. Okay, so we're going to use the integral to help us do that, because the integral is a limit of an infinite number of areas. So the setup for integration with respect to x means, okay, to find the area in this region, we have to know the lower limit a, the left x, and the right x. This tells us where we're going to begin and end accumulating all these vertical rectangles. And then all we need is the representation of one of the heights of any of the rectangles that are in here. So that would be the top curve minus the bottom curve. Okay, and then we would integrate. That's the width there of one individual rectangle, and we integrate, and that would sum all the areas and give us the answer to the area question. Something worth noting before we move on, because it'll come up later, is this. When you look at this region right here for this particular graph that I drew, notice that no matter where you inscribe your random rectangle, if that's my rectangle, that every rectangle that I inscribe in here, okay, every rectangle, okay, always touches the top curve, and the bottom of that rectangle always touches the bottom curve. Okay, we don't have a switch. And this will come up later. So this rectangle, the top touches F, the bottom of that rectangle touches G, the top of this rectangle touches F, the bottom touches G. And that never changes as you travel from left to right, from A to B. And we want to be on guard for when that may change, because how we handle the integral will depend upon that situation. Okay, now let's take a look at integration with respect to y and what that means. All right, to help us with our work, let's also get a graphical representation of this situation. Okay, I'm going to draw two random curves. They may or may not be functions. Okay, but these equations that I'm going to be working with are actually solved for x. X equals something in terms of y. Okay, so I'm going to maybe have this random curve that's not a function. And then maybe here comes another graph, and it's going in here something like this, and continues downward. Okay, so for us, we may be interested in finding the area, say, from this starting horizontal line right here up until we get to this natural intersection point right here. Okay, so let me call this first graph that I drew x equals f of y. So it's an equation solved for x in terms of y, and let's call this one x equals g of y. Okay, so you may or may not have functions. This one doesn't appear to be a function, but this one may be if there's no more interesting behavior that loops it around. Okay, well anyway, if we have two equations and they're both solved for x, x equals something in terms of y, okay, then this is not integration with respect to x, it's with respect to y. Okay, so maybe this y value right here is some number, and I'm going to call that c, some low c value. Okay, now we need to be mindful of this point of intersection right here, and we need to be aware of what its y value is, and we'll call that d. So integration with respect to x, we look at limits of a and b. Integration with respect to y means we're accumulating rectangles from c to d, so horizontally speaking, I guess. All right, so to find the area in this region, which is what we're interested in, we're not going to put vertical rectangles in here, we're going to put horizontal rectangles in here. So maybe somewhere along the way here, about right here, okay, we have a rectangle. Here we have another rectangle. Here we have another rectangle. Okay, we have an infinite number of rectangles that are laying flat, horizontally. Okay, if I can find the area in one of them, or at least a representation of the area in one of them, I can use the integral to help me find the area in all of them, which gives me the area of the total region. So in this case, if we're going to look at, say, this arbitrary rectangle right here, okay, and we want to find the area in this rectangle, we would need to know the base and the height. Well, I'm going to look at the thickness here. If you look at the thickness of this rectangle right here, we're going to not call it dx, a change in x. I mean, it does have a little bit of thickness, but it's actually the change in y. So maybe the rectangle is only this wide right here. So that difference right there, or that change, is called dy. So the area in this horizontal rectangle, okay, is its base, dy. Okay, its base, I guess we can call it. It looks like a height, but we'll call it a base. And then its length right here. Okay, well, what's a representation for this length? Well, over here, the right side of the rectangle touches the x equals g of y curve. Okay, it's g in terms of y. That's the x value. Okay, and over here, this x value right here is f of y. So what we're going to do is a right x minus a left x, because if this x is bigger than this x right here, then if I take the right x and subtract the left x, I'm going to get a positive distance. And we want area to be positive. Okay, so the expression that represents the length of this rectangle is right curve minus left curve, or g of y minus f of y. And it's important to take note of the situation that we have all, the whole expression in terms of y, whereas in the previous example, our whole area expression was in terms of x's. Okay, so then we're going to use the integral. Now notice the limits are y limits and not x limits. Okay, so my low y is c, my high y is d. Okay, I'm going to add up all the areas from c to d. Okay, and then the area in one rectangle is the right x, this x, minus the left x, okay, times the width, which is dy. I think again it's important to take note of the fact that no matter what rectangle you inscribe in here, that every single rectangle on its right side will always touch the g of y curve, and every rectangle on its left side will always touch the same other curve, f of y. There's no change. Okay, and I say that just to get us ready for an example so that we can handle it differently. So this is the background on how we're going to find area between two curves. So it's important to know how they're oriented. If it's with respect to x, we should see a situation where we have two equations, y equals. We figure out what's on top, we figure out what's on bottom. We do top minus bottom in the integral. We pay attention to the limits, the x limits, from a to b. For integration with respect to y, we pay attention to the functions, which one's on the right, not the functions, the graphs, excuse me. We pay attention to which graph is on the right to get a right x and which one's on the left so we can set it up appropriately, right x minus left x, and then we integrate with respect to y. And of course you pay attention to the limits too. So we need to look at some examples. So in example 1, if you're given this as your problem and you're asked to find the area between the two curves, and that's all you're given, okay, you need to produce a graph if a graph's not provided so that you can see which function's on top, which function's on bottom, and so you can see what the left limit and the right limit are so that you can set up the integral and then do the calculations to find the answer. Okay, so you could either graph this if you have a calculator, y1, y2, set a good window that shows a visual of where these graphs kind of compare with each other. But real quickly, based on our background, we know this is a parabola that opens down. Its vertex is at 0, 2. Okay, we also know that this is just the linear function y equals x, g of x equals x. Okay, so this is f of x, and the linear function is g of x. So it's clear that we can see that a natural bounded region is created between these two curves. Okay, so the x-coordinate of this point of intersection would be our a value, our far left value, and the x-coordinate of this point of intersection would be our far right value, x value. Okay, so now we know the limits of our integral. We also know that through the visual we have f on top and g on bottom, so we can set up the integral. Okay, the only problem here is finding these x values of these points of intersection. Certainly if you have a calculator to find these points of intersection, just graph and then find them from the calculator. Without a calculator, it's probably worth taking the time to remind ourselves how we would find those points of intersections. Okay, so I'm going to just write this down here. Intersections. X-coordinates is what I need. Okay, well that would just require us to set the two equations equal to each other where they intersect. And from here, algebraically, it's quadratic. Okay, I'm going to set the equation equal to 0. And the reason I'm pulling both of these terms to the other side is because I noticed that x squared is negative here, and if I move it to the other side, it becomes positive. And I'm going to write it in an appropriate form here so that I could easily factor. Okay, so either x is 1 or x is negative 2. So what this tells us is that here x is negative 1 and x is negative 2 here and x is 1 here. So those are our limits, our x coordinates of our limits. So let me come up here. So what's the integral that would represent the area in this region? Okay, well, from left x, -2, to right x, 1, okay, we have our limits. The top curve is f of x, the bottom curve is g of x. And again, always want to pay attention to the fact that as you travel from left to right, stacking in your vertical rectangles, because we put in vertical rectangles with respect to x, because the thickness of each of these rectangles is a change in x, dx. Notice that no matter what rectangle you put in here, every rectangle at its top touches f of x, and every rectangle at its bottom touches the other curve, g of x. Only one integral is required to accumulate the area in all of these rectangles. So it's f of x minus g of x. So f of x minus g of x with the change in x. And I'll just say right here, if you were just to put the notation in the integrand, f of x, and then g of x for x, that's totally acceptable. You would get full credit for that setup. So it's all about the setup that represents the area. Okay, and you can use the names they give you, or you can actually put in the specific equations. Okay, at this point right here, you could either go to your calculator, type this into y1, go to the home screen, do the necessary keystrokes, and get the value of the integral. Okay, or by hand, you can find the antiderivative and evaluate at the endpoints. Okay, so I'm going to go ahead and do this one by hand. So the antiderivative for 2 is 2x. X squared becomes x cubed divided by 3. And the antiderivative for x is x squared over 2. Okay, we're going to take that whole antiderivative and evaluate it from -2 to 1. Alright, so plug in the upper limit, so that's 2 minus 1/3 minus a half. Evaluate the antiderivative of that x to get that y, so that's 2 times -2 or -4. Plugging in -2 results in -8, so that's plus 8/3. And plugging in -2 and squaring it gives us 4 over 2, so -2. And let's clean all this up right here, and when all that is said and done, we're actually going to get 9/2. So that's the area in the region. No mistake was made. We do have a positive number here, 9/2. If you did end up getting a negative answer, just some things to look for. It could have been that you evaluated your limits in a reverse order. That would result in you getting a negative number. Or the second kind of thing that to put on your radar is, how else would you get a negative number, is maybe you had G on top and F on bottom. And so you had these backwards, which would result in a negative number. So just to point out some things there, some red flags, if you do get a negative, where you might want to go back in your work and check to see where that occurred. Okay, so we're going to have to use another video to do some more examples.